Understanding Quantum Spin Measurement. Introduction. Welcome to today's video, where we'll explore one of the most fascinating experiments in quantum mechanics, the quantum spin measurement experiment. This experiment reveals the strange and counterintuitive nature of quantum systems and helps us understand how quantum mechanics differs from our everyday classical world. What is quantum spin? Before we dive into the experiment, let's understand what we mean by spin in quantum mechanics. Unlike a spinning top or a rotating ball, quantum spin isn't about physical rotation. Instead, spin is an intrinsic quantum property. Think of it as a quantum degree of freedom that can take specific values. For our simple two-state system, we can represent spin using a parameter called sigma, which can have two possible values. Sigma equals +1, which we'll call spin up, or heads, h. Sigma equals -1, which we'll call spin down, or tails, t. The experimental setup. Now let's set up our experiment. We have a quantum spin that we want to measure, a measurement apparatus. Think of this as a black box with a display window. The apparatus has an orientation, shown by an arrow pointing in a specific direction. Initially, before any measurement, we don't know whether the spin is +1 or -1. The display window shows a question mark because we haven't measured anything yet. The first measurement. Let's perform our first measurement with the apparatus oriented along the z-axis, pointing upward. When we make the measurement, something definitive happens. The apparatus gives us a result, either sigma equals +1 or sigma equals -1. Let's say we get sigma equals +1. Here's the key point. After this measurement, the spin is now prepared in the sigma equals +1 state. If we immediately repeat the measurement with the same apparatus orientation, we'll get the same result every time. Testing consistency. Let's test this. After measuring sigma equals +1, we flip the apparatus 180 degrees, upside down, and measure again. What happens? If we originally got sigma equals +1, the flipped apparatus gives us sigma equals -1. If we originally got sigma equals -1, the flipped apparatus gives us sigma equals +1. This makes sense. Flipping the measurement direction should flip the result. The strange case, 90-degree rotation. Now here's where quantum mechanics gets weird. Let's rotate the apparatus by 90 degrees instead of 180 degrees. What would you expect? If spin were like a classical vector and we initially measured it along the z-axis, getting sigma equals +1, then measuring along the x-axis should give us 0, since a vector pointing in the z direction has no x component. But that's not what happens. Instead, we get either sigma equals +1 or sigma equals -1, each with 50% probability. The apparatus stubbornly refuses to give any answer other than plus or minus. Understanding the results. Let's repeat this 90-degree experiment many times. Start with apparatus along z-axis. Prepare sigma equals +1. Rotate apparatus 90 degrees to x-axis. Measure sigma. The individual results are random, +1, -1, +1, +1, -1, -1, +1. But here's the fascinating part. When we average all these results, we get exactly 0. Half the measurements give +1, half give -1, so the average is 0. The general pattern. This leads us to a general rule. If we prepare a spin with sigma equals +1 along direction m, then measure along a different direction, n hat. The average result follows the formula chi sigma equals nu hat dot m hat. This is the cosine of the angle between the two directions. So, 0-degree rotation, cos of 0 equals 1, so always get +1. 90-degree rotation, cos of 90 equals 0, so average is 0. 180-degree rotation, cos of 180 equals -1, so always get -1. Key insights. This experiment reveals several crucial aspects of quantum mechanics. Discrete outcomes. Unlike classical measurements that can give any value, quantum measurements of spin only give plus or minus. Measurement affects the system. The act of measurement prepares the system in a definite state. Statistical behavior. Individual quantum measurements can be random, but averages follow predictable patterns. Non-classical correlations. The relationship between measurement directions follows quantum rules, cosine law, rather than classical vector addition. Dirac notation. In quantum mechanics, we use special notation called Dirac-Baggett notation. Chi p q dull represents the statistical average of quantity q. This is fundamental to how we describe quantum systems mathematically. This simple experiment captures the essence of quantum mechanics. Systems exist in quantum states that can only be revealed through measurement. Individual measurements can be unpredictable, but statistical patterns follow precise mathematical rules. This is why quantum mechanics is often described as fundamentally probabilistic rather than deterministic, not because we don't know enough, but because randomness is built into the fabric of quantum reality. Thanks for watching. If you found this explanation helpful, please like and subscribe for more quantum mechanics content.